Recall we can take the square root of a number, and this technically equals plus or minus 3, but normally we just say this equals 3 and just only consider the principal root. That way we only get one result for our result in here. So this behaves like a function. Well, anyways, if we have a situation like that, what happens when we have my drawing pad is starting to misbehave. What happens when we have something like this, where we have square root of minus 1? What does this equal? Well, there are no two numbers when you multiply them together. There's no two real numbers when you multiply them together that equal minus 1. For example, if you took minus 1 times minus 1, well, this equals a positive 1. And so this does not equal that. It also does not equal a situation, obviously, of 1 times 1. That also equals 1. So there's no two numbers you can grab that you multiply together to equal minus 1. So what we need to do is we need to make up a new number. And that's what mathematicians have done. So if you take the square root of minus 1, it makes up a new number, and we have to assign a symbol to the new number, since we don't have any actual real numbers to represent it, and the symbol that is assigned to it is I, or sometimes J. In the electric field, a lot of times they use J because, well, we'll discuss why later. But in this situation then, I times I equals negative 1. That's what it's defined to be. That's what the number is defined to be. So this I is what we call an imaginary number. It does not exist on the real number line. And recall, on a real number line, we have our integers 1, 2, 3, going out to infinity. We have negative integers. We have rational numbers, which are integers divided by integers. Sometimes those rational numbers go on for infinity. 1 divided by 3 equals 3.33333 for infinity. And then we also had the irrational numbers, like square root of 2 or pi. This made up our real number set. Well, like I said, I does not belong anywhere on this real number line. But I, in itself, just equals, this is going to irritate me if this continues. I is the same thing as, say, 1, the number 1, times I. And in fact, we could take any number times I. We could take 3 times I, and we end up with 3i. So we can operate on I in this way, or we could take minus 2 times I and get minus 2i, or we could take 3.2 times I and end up with 3.2i. Or we could even use a fraction, 1/2 I. 1/2 times I is also an imaginary number. So we could set all these up in a number line where we also have a 0 value, because I times 0 is still 0. Follows that rule. But now we have in our number line 1i, 2i, 3i, so on and so forth, out to infinity I. But this is our imaginary number line. It's not the real number line, it's the imaginary number. Minus I, minus 2i, so on and so forth. We could have a 3/2 I here. We could have a pi times I here, so on and so forth. So anything we could have, any real number that we have in the real number line, we could multiply by I and get an imaginary number in our imaginary number line. And since we can do this, this enables us to solve more complicated imaginary number problems, like the square root of minus 9, for example. If you think about it, there are no two real numbers that you can multiply together to get minus 9. But we could turn this into the square root of 9 times minus 1 excuse me, equals the square root of 9 times the square root of minus 1. Again, taking the principal root of the square root of 9, this equals 3 times, and the square root of minus 1, as we said before, equals I, so this equals 3i. So in general, we can take the square root of any two factors, one of which could be a negative number, and end up with the square root of a times the square root of b. However, there is one exception to this rule. So the square root of a times the square root of b equals the square root of a times the square root of b, only if a is greater than or equal to 0 and both b are greater than or equal to 0. Why is this? Well, let's show you. Let's look at it. So if we take the square root of minus 6 times minus 6, so here, this is the exception. This equals the square root of, well, minus 6 times minus 6 under this equals 36. And this equals 6. The principal root of that is 6. But on the other hand, we're going to see that it does not equal 6 if we perform this operation up here. So suppose I split this up, minus 6 times the square root of minus 6 equals the square root of 6 times the square root of minus 1 times the square root of minus 1 times the square root of 6. So this then equals, well, I can take these two square root of 6's and combine them. Square root of 6 times 6. And this is equal to I. And the square root of minus 1 over here is also equal to I. So the square root of 6 times 6 is 36. The square root of 36 is 6. And I times I is I squared. And we know that I times I is minus 1. So this equals 6 times minus 1, or minus 6. So we see that this does not equal, essentially this does not equal this. So this is an exception to this rule when we're dealing with negatives under R. And it only occurs when you have both of these values are negative. So I gotta keep that in mind. But otherwise, we could solve a number of different problems, like in addition to the square root of minus 9 equaling the square root of 9 times the square root of minus 1, which equals 3i. We could have the square root of minus 0.25, for example. And we can perform the same idea. The square root of 0.25 times the square root of minus 1 equals the square root of 0.25, which is 0.5 times I. 0.5i. Let's just do one more. Square root of minus 3 equals square root of 3 times the square root of minus 1 equals I times the square root of 3. I put the I first because it could be confusing when you have a radical. Now we can also do more complicated problems like the square root of minus 75. And this equals square root of minus 1 times 25 times 3. 25 times 3 is 75, which equals, so now I can break all of these off. Square root of minus 1 times the square root of 25 times the square root of 3. So this equals 5 times the square root of 3i. Put a little dot in there to indicate that it's because the square root of 1 is I, square root of 3 is 3, it's irreducible, and the square root of 25 is principal root is 5. Notice I could have a situation where I could have minus the square root of minus 75. Well, in that case, we would do the same thing we did over here, but we would end up with minus 5 square root of 3i, or just minus 5 square root of 3i. So, as a final note, let's look at what happens when we take I and multiply by itself. So we start out with I equals I equals, and if I take I and I square it, that equals minus 1, as we said. But now if I take I and I cube it, well, that's going to be I times I, which is minus 1, times I equals minus 1i, or minus I. And if I raise it to the 4th power, well, we're going to get I times I times I times I, which is like minus 1 times minus 1 equals positive 1. So this is a positive number. We don't have to put the positive in front of this. So now I'm going to put a line here because this process just repeats. So I to the 5 is essentially I to the 4th times I, or 1 times I equals I. So it's the same as this now. And I to the 6th equals, well, it's essentially I to the 5th times I, so it's I times I times I. So this ends up equaling minus 1. That's this next one. And it just keeps cycling like this on forever. I to the 7th equals essentially minus 1i, or minus I. And then I to the 8th. So every 4, it finishes up again, and then we'll start repeating after that equals 1. And that's all I have time for right now.